Alright guys, as promised, I'm going to talk about example 1 and the relevant parts of this equation that you saw at the end of the last video in a little bit more detail by showing you the pieces of a couple of different capacitors. So to start with, we have these pieces of aluminum foil. Well, that would be like the plates of the capacitor. All right, now you all know how to calculate area, right? If it's something like this, right, we might do, say, length. It's supposed to be an L. Length times width. Or if it was circular plates, you might use, say, pi r squared. All right. Don't double the area. You can't see anymore what I wrote there, but it's the area of just really one of the plates. Okay, so there's always going to be two parallel plates in a capacitor. Always two. And the way the formula is done, the A there is really just the area of one of the plates. Now, what I'm trying to demonstrate with this picture is the denominator there, the D. The D would be the separation distance between the two plates. So I did my best here to hold the two plates at some particular uniform distance apart, but that right there would be the separation distance. Obviously, this would be better if I had, say, like stiff pieces of metal as opposed to floppy sheets of aluminum foil that could be many different distances apart at different points. Okay, but I think you get the idea. Separation distance. And here I am showing you the dielectric. Now, in the previous picture, the dielectric was air. What was in between the plates? Well, it was air. Never say nothing. I mean, I suppose we could have a vacuum in between the plates, but usually there's something in between the plates, unless it's very special circumstances. In this case, the thing in between the plates, which is always the dielectric. That's what that word is. The dielectric is the thing in between the plates. The dielectric would be paper. And so the dielectric constant would be some number that you would look up that would be whatever it happens to be for paper. There's probably a lot of different ones for paper because paper isn't one thing. All right, there's a lot of different papers. Right? There's wax paper, there's cardboard, there's bleached paper. It's probably even a little bit different if it's, say, got stuff printed on it, all right, or if it's glossy paper, all right, but whatever, paper in this case. Also note that the plate separation in this case would be a little bit different than what I showed you in the previous picture. In the previous picture, when it's air in between the plates, you know, it's just, well, you're looking at the two plates and how far apart they are. But in this case, the plate separation is the thickness of a piece of paper, which is going to be a pretty small number, as you might imagine. Now, here I had a piece of foam board that was just sort of lying around. If I used foam board as my dielectric, it's going to provide a different result from paper for two reasons. I think you can appreciate that the foam board is significantly thicker than paper is, right? If that were paper, the distance might be, I don't know, like a few micrometers, okay, like, I don't know, 200 micrometers, which would be a very small plate separation indeed. In this case, the plate separation is probably about like 0.6 centimeters, right, which is significantly thicker than for a piece of paper. So D then is obviously going to be different if I'm using a foam board instead of paper. The other thing though that changes is the dielectric constant. So if I start messing around with the dielectric, if it implies something about the plate separation changing, then you have to worry about D, but usually the thing that's most directly changing is the kappa right there. Oh, I didn't mention one very important thing about kappa, which I guess I'll mention now, since I just remembered. Don't call it K. Mr. Erico, it looks like a K. I know it looks like a K, but it's a kappa. And the reason I want you to think and say kappa is so that you don't end up putting in K, Coulomb's constant. Remember Coulomb's constant from last unit? It was 9 times 10 to the ninth. I shudder to even say that number under these circumstances. For behold, you will never, ever plug in something as large as 9 times 10 to the ninth for kappa. Air is 1. Paper is probably something like 2.5. Styrofoam might be, I don't know, 3.6. I don't know the particular values, but note, I'm saying smallish numbers. 9 times 10 to the ninth is enormous. Kappa will never, ever, ever be that big. Okay, so the two things I wanted you to get from this, the plate separation is usually however thick the dielectric is. And also, the dielectric constant is going to change depending on what the material is in between the plates, because the material in between the plates is the dielectric. And here, just for the sake of showing you one more example, you can barely even see that clear cellophane wrap. Okay, which would be different from paper, because it's a different thickness, presumably. And also, it's not paper, so kappa will have a different value. And so any real dielectric could be made from any of these various components. A dielectric needs two conductive plates. It needs a dielectric in between them. And then everything else just kind of varies. You can make those metal plates any size you want. Your dielectric might be of a variety of thicknesses depending on exactly what parameters you want for your capacitor. When I showed you the real capacitors before, like the ones that you might actually say use in a circuit in the previous video, imagine, so obviously those don't look like this, right? Imagine taking this though and rolling it up really small, right, into like a really tight cylinder. Well, that's approximately what those things are, okay? Any commercial capacitor is going to be a lot better than this because they're doing the variety of things that are going to make it way, way more compact, all right? Notice, you can't see it in the equation right now, but I'll circle it anyway. The D, the smaller the plate separation is, the smaller that is, the bigger the capacitance is going to be. So as D goes down, the plate or the capacitance increases. So the closer together you can get those plates, the larger the value of the capacitance is going to be for your capacitor. And then also, obviously, a larger dielectric constant and a larger surface area are going to have the same effect of increasing the capacitance. Now, at this time, you should go ahead and find example 1. I won't have the prompt up on the screen for the most part, so you should have that notes packet out in front of you so you know what the prompt is. Now, the prompt says that we're supposed to go measure a capacitor at the front of the room. Well, lacking that particular convenience, here I have some circular pieces of foil that I cut out to pretend to be a capacitor. And looks to me, if if I lined everything up carefully enough, the diameter of those metal plates is 11.9 centimeters. Okay, I'm going to have to make up a number for the plate separation since there's not really a great way to do that otherwise. Now, it's asking us to calculate the capacitance 9 out of 10 times. If they say calculate the capacitance, this is the right equation to use. So I measured the diameter so that I'd have something to plug in for the surface area. And presuming that the plates were, held up a particular distance apart, like they would have been had I been able to use my capacitor at the front of the room, the dielectric would have been air, for which the value is 1. Now, if you're thinking, where should I find the value of the dielectrics? Air is the only one that I expect you to just basically know. Anything else, you can Google dielectric constant and then whatever the material is, and you should be able to find it. Okay, depending on the object, right, whatever shape the plates happen to be, they might tell you it's a circle or a rectangle or whatever. You'll use a different area function. So these were circular plates. So pi r squared. Okay, not 2 pi r. If you're thinking 2 pi r, I remember that one also. That is the circumference of a circle, not the area of a circle. So pi r squared. Okay, so note, convert it to meters. I said it was 11.9 centimeters. Careful with that. And then what I actually measured was the diameter. All right, most of the time in a problem I'm not going to be that tricky. But you know, if you're working with real measurements, you got to remember, here's how I actually usually find the radius, is you measure the diameter and divide by 2. And here I am just making up a number for the plate separation. So if those pieces of foil were held a uniform distance of 1 millimeter apart, then I would put in, notice that's a number in meters. Just like how I need to use meters when I plug in to get the area, the plate separation has to also be in meters. And the value of epsilon naught is 8.85 times 10 to the negative 12th. Epsilon naught is called the permittivity of free space. That is not a name that I need you to know. But that's what it is permittivity of free space. And its value is 8.85 times 10 to the negative 12th. So small little number. And it's a constant. You're fine. That's all you really need to know about it, is just you have to have it to plug it in. And we're ready to calculate. So pause the video, type in the numbers yourself to make sure you know how to make this all work in your calculator, and see what answer you get. Boom. 9.84 times 10 to the negative 11th farads. Okay, I frequently get some confusion on the units because I know C is the abbreviation for coulombs, and it's the variable for capacitance. Alright, I'm sorry. Somebody in physics should have tried to keep that a little more straight or whatever, but yeah, so you just got to remember C is the variable for capacitance and also the abbreviation for coulombs, which is the unit of charge, and capacitance is measured in farads, which is a coulomb per volt. Once you've calculated the capacitance of the capacitor, we can move on to part B, which wants to know what is the amount of charge that we could put on this capacitor at 3,000 volts? Okay, well, for a question where it's having you relate charge and volts and capacitance, then the relevant equation to use is C equals Q over V, which brings us back to the definition of capacitance being a coulomb per volt. So we're not going to get a lot of coulombs on this thing. That's a tiny little capacitance down here, right? Even though we're putting 3,000 volts on it, it's not going to be a lot of charge. All right, but fine. See if you can rearrange that equation to solve for Q. Meaning, of course, pause the video and solve for it. Pause. Now that you have resumed, here is the answer. Wonderful. Okay, on to part C. So hypothetically, if paper were used instead, nothing much would change. I suppose the thickness of the paper might end up being the plate separation. But if the problem is described in such a way where like you don't know the thickness of the paper, then our assumption is just whatever the plate separation was before, it's just now filled up with paper instead of being filled up with air. Okay, so we won't change the plate separation or anything. And then the thing that will change is the dielectric constant, right? Because it says it's paper, not air now. The dielectric constant of paper, according to my one of my various textbooks, is 3.7. All right, well, if air was 1 and paper's 3.7 and nothing else is changing, then that just means the capacitance is going to be larger by a factor of 3.7. And so I will get this answer without all the fuss of typing everything back in again. Just multiply by 3.7, and there you are. All right, now the question didn't ask how much charge could you put on this capacitor at 3,000 volts, but it would be the same basic calculation as what we did before in part B. You would just use the new capacitance. Okay, that should be everything you need to know for the homework. Please comment in the discussion post.